Hi folks, Mr. Ackerman here once again. The topic of today's video is the speed of waves, and this is a topic that we've sort of touched upon when we did some introduction to waves, but we didn't really talk about it too much. All we did was notice that waves, such as water waves, or even the wave at a baseball game, moves, and if it's moving, then I'm sure you have a sense that it must be moving with some speed. But today we're going to talk about how you actually measure that speed, what formula can be used, and also once we get through that, which shouldn't take too long, we're going to get into the really interesting part of this section where we talk about something called the Doppler effect and some of its applications. So first of all, let's close out this screen, and first I want to jump to YouTube for a moment, and I just want to show you, this is something I found, I wasn't aware they had this, but if you want to go surfing in the middle of the desert, all you got to do is hop a plane to Dubai, where they've built this humongous wave pool, and I'm going to play the video for you now without any sound. This is what people are doing out in the middle of the desert in Dubai, and I don't really want you to focus on the surfer. What I want you to focus on is that wave that's moving. If a wave is moving, and I were to ask you how fast is it moving, you could use an idea that I'm sure you learned a long time ago in school, or maybe you just intuitively know what the idea is. The idea is quite simple, actually. Very simply, you can say speed equals distance divided by time. I'm pretty sure most of you know this formula. It's a very basic formula. And what you might not know are what are the symbols that we use. Well, maybe you've seen this, S equals d over t. Maybe you saw that in math class. And that's fine, but actually in the textbook that we have, we don't use the letter S for speed, so I'm going to erase that. We use the letter V, and I'm not trying to confuse you by using V instead of S. The V actually is related to the word velocity, which is another word that's related to motion, and we haven't gotten to it yet in this course. We will get to it in the not too distant future, but the V comes from velocity, which is related to speed. Just so you know where that letter comes from, now you're going to be able to follow along with the textbook symbols, and you'll be okay. Remember how we've been using delta t for time, the Greek letter delta? Well, we also use a delta d for distance, and again, when we get to the part of the course where we talk more about speed, distance, and time, that'll become obvious why we use that. But for now, take my word for it. This is the symbol. It still means distance over time. Now, if you're talking about a wave, you might wonder, well, what are the wave characteristics that relate to distance? And the answer for distance, if you think about a wave goes through its cycles like this. It goes up, it goes down. In a certain amount of time, it travels a certain distance. Well, that time and distance are related to its cycle, and therefore, you may have guessed, the time is actually the period of the wave, and that was capital T, remember, and delta d, the distance that a wave moves in a cycle, is actually the wavelength, the distance from one crest to another crest, or the distance from a trough to a trough, or really the distance from any point on the wave to the very next point that's in phase with that. So for example, these 2 points that I kind of randomly chose, any of these distances would all be the same. If you guessed lambda, the wavelength, you are correct. So delta d, the distance traveled in one cycle, is lambda. Lambda over delta t, that's it. We just found the formula for calculating the speed of a wave. You just take its wavelength in meters, divide by the period in seconds, and you're done. So I'll write that over here as one neat formula, and I'll circle that one in red, put a box around it. One other thing to remember, because 1 divided by t, the period, is frequency, well look, we have t in the denominator here. That's the same as 1 divided by t. So we can actually replace the 1 over t that's written in here with frequency, and that'll give you another version of the formula, which is frequency times lambda. And this is the more common form of the equation that you'll see written in your textbook. And this is known as the universal wave equation, or I like to write UWE because I'm lazy like all physicists and I don't want to keep writing universal wave equation. That's it. Speed equals frequency times wavelength. There's a sample problem in your textbook that you should check out, and this is so straightforward and self-explanatory that I'm not going to waste any more of your time with this. This formula calculates the speed of any wave if you know a couple of its characteristics. That's where we're going to leave this. I'm not going to do a calculation for you at this time. What I do want to point out, which is really interesting, are the applications or the consequences of this formula. So going back to what we said we were going to discuss, how do we measure the speed of a wave? Go to Dubai, watch someone surfing, measure how fast the wave moves by calculating the distance it travels in a certain amount of time. And oh, by the way, if you happen to know a little bit more about the wave, like its frequency and its wavelength, or instead of frequency, maybe you know its period, plug the numbers into this formula. See the example problem in the textbook for a sample. Okay. Now, something that is worth noting is that when a wave is traveling through a medium, for example, sound waves are traveling through air or water waves are traveling through water, it is true that the waves have a certain speed which is actually constant. So let's close this out for a second and go to another page here. Let's just write that down. Waves travel at constant speed in a given medium. Now, if you are in my class, then you will have done at this point a sort of little investigation involving slinkies. And in the slinky investigation, we send waves down a slinky and we measure their speed and we try to answer the question, does the speed of the wave ever change? And if you think back to what we discussed in class, then the answer actually is they don't, unless you actually stretch the slinky a lot more than normal or you unstretch it a lot more than normal. In other words, the speed of a wave is constant as long as we keep the medium, the substance the wave is traveling through, constant. So let's look at what that means. Since we know that v equals f lambda, well, therefore, this number is a constant, the speed. So a constant is equal to frequency times wavelength. So something interesting that happens is when you take a wave that's moving at a constant speed, if you increase the frequency, well, since you're multiplying that by the wavelength, to keep that product constant, the wavelength has to go down. And conversely, if you decrease the frequency, since you're multiplying that by another number to keep the product constant, the wavelength will have to go up. And now, where have we seen this before? If you think back to something that we talked about in the previous wave video about wave characteristics, I showed you the electromagnetic spectrum, and we talked about radio waves, infrared, ultraviolet, X-rays, and so on. And I showed you that at one end of the electromagnetic spectrum, at the radio end, there were waves that were very spaced out, like that. But as you made your way toward the X-rays and the gamma rays, the waves that they drew in this diagram started to bunch up much closer. Now I know this is a terrible drawing here, I apologize. But the point is that some electromagnetic waves had a very long wavelength. and some of them had a very short wavelength. Well, go back and look at that diagram, which actually is in your textbook if you want to look it up, or you could go on Google and all you got to do is type in electromagnetic spectrum. I'll show you how easy it is. Just go like this. Oh, see, I've already got it in there. Electromagnetic spectrum, and look under images, and in virtually all of these images you're going to find something that looks like this. Here we go, let's take a look at that. Look familiar? We've seen this before. Radio waves have a very long wavelength. Gamma rays have a very short wavelength. Well, guess what? Look at the frequency of these waves. Very low frequencies for the long wavelength waves, and very high frequencies for the short wavelength waves. So if you go back here and you think about what we just said, that makes sense. Long wavelengths, big wavelengths, low frequencies. Short wavelengths, high frequencies. All right, so that's an interesting observation there. Something else that gets even more interesting is what is another consequence of the fact that waves travel at a constant speed in a given medium. If you take a look in your book, you will find a diagram in this section, a couple diagrams. So these diagrams, by the way, I want to give credit where credit is due. These diagrams are from the textbook Physics 11 by Addison Wesley. That's where I'm taking these two from. Imagine this. Imagine an object which gives off waves. This could be, for example, a train that's blowing its horn and giving off sound waves. Suppose it's moving. That's what this arrow here shows. And it gives off a wave, which is indicated by this crest. And of course, waves spread out. So a short time later, this wave has grown into a wider crest. If you imagine throwing stones into a pond from a bridge and looking at the waves as they spread out in circles like this. So the first wave that the train gives off when the conductor blows the horn spreads out like this. But the train is moving, so in the time that this wave takes to spread out, the train moves from point A to point B, and now it gives off another sound waves. It's continuously giving off sound waves because it's always making noise with its horn. And then this wave, B, grows into a bigger circle, and in that time the original wave from point A has grown into an even bigger circle. Meanwhile, the train continues moving along, and eventually it gets to point C where it gives off yet another wave crest. And what you end up with is something that looks like this diagram here. A whole bunch of waves spreading out all around the train, but they're kind of offset because each new wave is produced a little bit further on to the right. This is in contrast to the train, let's say, if it were at rest in the station just blowing its horn. If it weren't moving, then the waves would spread out in all directions evenly. But because it's moving, you get this lopsided result. Now let's analyze this using physics. Take a look at these wave crests. Remember, the wavelength is the distance between any two crests. Going back to this diagram here, you can see that the wavelength of the waves that are in front of the moving object are shorter than they are in the back. Here they are longer. So what does this mean? This means in the back, the wavelength is longer, lambda, but in the front, the wavelength is shorter. Well, let's look back at what we talked about just a moment ago. Because the speed of a wave is constant in a given medium, if one of these variables goes up, the other one has to go down because they've got to multiply out to the same number. So guess what? Wavelength goes up, gets bigger, frequency goes down, gets lower. Here, wavelength gets shorter, frequency must get higher. Now remember, I was talking about a train whistle example. So obviously we're dealing with sound waves. What does it sound like to us when the frequency goes down? Well, musicians know that low frequencies are low pitch. These are low notes like ba. And if the frequency goes up, then these are high-pitched notes like eek. Sorry, I'm not much of a singer. I apologize. You can all laugh at me in class tomorrow about the weird noises I'm making on the video. But the point is, if the train is coming toward you, if you're standing in front of the train, you hear a high pitch. If you're standing behind the train, you hear a low pitch. The sound of the train whistle changes depending on where you are, if the train is moving. Let's watch a video that explains this, or actually shows it, so that you'll know I'm not making this stuff up. All right, this video is something that I recommended you take a look at in your homework schedule, so do check it out. Just going to turn up some volume here. Ready? This is a video of a train approaching a railway crossing, blowing its horn, and you're going to hear higher pitch as the train approaches, lower pitch once it passes. Here we go. Okay, so there you have it. Now, that phenomenon has a name. It's called the Doppler Effect, and it applies anytime you have a wave source that is moving and someone is observing the motion of that source. Okay, so what are some other applications of this? Some really neat stuff, actually. One of them is radar. I'm sure you've heard of radar. What does radar stand for? It stands for radio detection and ranging. And radar is very interesting. It's got an amazing history dating back to around World War II. You should definitely check it out if you're interested in the military or just history in general. However, for us, let's talk a little bit about how, for example, police can detect whether you're speeding in your car. Air traffic controllers at the airport can help figure out where the planes are going and make sure they land safely. The military can conduct its operations, and even the weather forecasters can make predictions about what the weather is going to be. So we'll give you a quick example, and we'll open that up over here. Suppose you are, let's draw the ground here. You're on the ground, and you are an air traffic controller at the airport, and on the roof of the air traffic control tower is a radar dish. I hope I drew that okay. Anyway, this device sends out radio waves, which we've already talked about, and they have a certain wavelength. So when they go out, each of the crests is a certain distance apart, and if you measure the distance between the crests, you get what is called the wavelength. Now suppose there's an airplane flying, which there probably should be near an airport, and let's say the airplane is going this way. What's going to happen to these outgoing radar waves, the blue ones? Well, they're going to bounce off of the airplane, and they're going to come back. So I'll draw the ones coming back in a different color so that you can compare. They're going to bounce back, they're going to reflect and make their way back. Actually, I don't want to use that. That's too close to the ground color that I used. Let's use red. So back they go as they bounce off. However, each new wave that bounces back from a closer position than the previous one because the plane, which is doing the reflecting, has moved closer. So these waves that are coming back are actually going to be closer than the blue waves that were going out in the first place. And I'm going to do a demonstration of this for you in class using a slinky, but for now, hopefully I can get you to at least consider the idea that the wavelength on the way back will be lower than the wavelength was on the way out. And remember, When the wavelength is high, the frequency is low. And on the way back in, when the wavelength is low, the frequency is high. So the air traffic controller, she's sitting at the desk there and she's looking at what the computer's telling her about the waves that are coming back, and she sees, the radio waves that are coming back have a higher frequency than the waves that I sent out. I wonder what that means. Well, of course, she knows right away what it means because she studied physics to become an air traffic controller. She knows it means the plane is coming toward her. And so that is one of the ways that radar works. It tells you the direction that an airplane is moving. So there's one interesting application. And what the police do when they're trying to catch you speeding, well, actually, they're probably not trying to catch you speeding. They just don't want you to speed in the first place. But suppose you are speeding, that's how they do it. They're actually looking at the return echoes of the electromagnetic waves and comparing their frequency to the outgoing frequency. It's how air traffic control, military, and even weather forecasters work. One final example of Doppler effect in astronomy, and you should look this up. I'm going to spare you some time without going into it too much. But when astronomers look out at stars and galaxies and whatnot, you might wonder, how can they tell whether any of these things are moving? After all, galaxies, stars, planets, they're so far away that even though they might be moving very fast relative to Earth, the distance that we seem to notice them cover in even sometimes years or decades is tiny. Think about an airplane that's moving really fast and it's really far away. It barely seems to move if you look at it. Well, that effect is even more noticeable in astronomy, where we're talking about galaxies that are countless kilometers away from us. So how do astronomers ever know whether something is moving or not? Well, they actually use their telescopes to analyze the light that's coming toward us. And in the same way that the radar people were investigating the return waves, in astronomy, when we use our telescopes, we look at the waves that are coming toward us from these stars and galaxies. And if they seem to have a lower wavelength, higher frequency than what we had expected, then we can tell they're moving toward us. And the reverse is true if they're moving away from us. Now, why is this called red shift or blue shift? Well, think back to the electromagnetic spectrum, which I bet you I can find. Let's see if I still have it. There it is. In the electromagnetic spectrum, waves that are coming toward you that we said are shifted to lower frequencies, that's the blue end of the spectrum. So we call that a blue shift. And if the thing is moving away from you, let's say a galaxy moving away, then its waves will be longer, which is at the red end of the spectrum. So they call that red shift and blue shift. And you should definitely check that out. Astronomy is very fascinating, and you can learn a lot just by studying it. One final thing that relates back to what we discussed here, where the speed of a wave being constant, sorry, that's not the one, there we go. The speed of a wave being constant in a given medium means that when the frequency goes up, the wavelength goes down, and of course that leads us to the idea of Doppler effect. Something very interesting can happen when a source of waves is moving. As you can see, the waves bunch up in front of the object, and that leads to the Doppler effect. But what if the object was moving so fast that the waves bunched up and the spacing became tiny, like the waves were actually touching? In this diagram, it would look like the wavelength in front was practically zero. What would that look like? Well, I've got another YouTube video for you to watch, and that one is over here. This one is also in your homework schedule. In this example, an airplane is flying. Airplanes make noise. They have their engines making noise, and they also disturb the air around them. And just like a boat going through the water produces waves that spread out, an airplane moving through the air produces waves that move out. This is an animation of what this would look like if an airplane were going by. It would actually push the air out of the way in front. The waves, or the pulses, would be very closely spaced, and you'd notice a very, I guess you could call it a short wavelength, and then in behind they would be stretched out. But watch what happens in this video when they have the plane go by one more time, this time at a higher speed, something very interesting happens. Now the plane is moving so fast that the waves in front actually bunch up. Now if this is the case, all that air that's bunched up in front is going to make it very difficult for the airplane to maneuver safely. And if that were to happen with most airplanes, they would quickly go out of control and crash. In the 1940s, the mid to late 1940s, when jet engines were starting to come online, airplanes were becoming powerful enough to go fast enough to actually do this to the air, and many of them actually spun out of control and crashed. It wasn't until an airplane called the Bell X-1 was produced in the United States. Here's a picture of it. It's actually in the shape of a bullet, and it's powered by a rocket. It wasn't until this airplane, it's called the Bell X-1, was produced that people were actually able to travel fast enough to punch through that bunching up of waves that you see here. Once they did that, here's what the video would look like. You'd actually be outrunning the waves that your airplane is producing. And this is what's called breaking the sound barrier. The cone shape, or the triangular, this would actually be in 3 dimensions, it would be a cone-shaped wall of sound waves or pressure waves. When they hit the ground, they create what's called a sonic boom. And so for those of you interested in some more interesting history and physics, military history, check out the sound barrier. Look up sonic boom. Learn about a pilot called Chuck Yeager. I hope I spelled his name correctly. He's the guy in here who was the first person in level flight to travel so fast that he actually outran the waves he was producing. He broke the sound barrier. He created the first sonic boom from an airplane, and he didn't die doing it. Very interesting story. Anyway, that's it for this video. I hope you enjoyed. Hope you can see that there is some interesting stuff in this section, and I hope you'll continue to do some additional research on your own, and we'll talk more in class. Thanks for listening, folks. Bye.